Well, it depends on how you count. All right, so we are now recording. This is this is our second day to talk about chapter 9. Um, and we already went through all the slides. So I guess the first thing I'll do is ask anybody if they want to review anything from the slides.
Can we go over the strengths of the lock-free versus the lazy?
Yeah, it's okay, let's go over the strengths of the lock-free versus the lazy. Actually, why don't I switch gears on it instead of doing the slides, I'll go to the code, which is what I kind of wanted to do. Um, so let me open that up on my laptop here. Oh, come on. All right. So we have all the different sets, and I've got them implemented here in this code. And you wanted to go through the lazy set versus the lock free. So what the lazy set is going to do, the key difference in the lazy set is it's going to set the marked bit, right? So when it deletes something, it's not just going to set the predecessor next to the current next. It's going to set cur.marked to true. And that says that cur is deleted. It's still going to do its locking. Oh, let me just fill you in on the weirdness of my code here. So what I did when I wrote this up is I was trying to cut down on the amount of coding I was doing. So I made this interface called found pred cur like this. And then in my lazy set, I create the I create I instantiate an anonymous inner class of type found, and it takes a predecessor and a current node and does stuff. And then there's a find method that each class implements. And in this case, what the find does is it starts at the beginning, gets a predecessor and a current, and while the current is less than the key, it advances, and then it it locks and it checks everything. So it locks the predecessor, locks the current, checks that the predecessor isn't marked, the current isn't marked, and the predecessor next is equal to the current. And if that's true, it calls found with pred cur, right? So I can just reuse this for add and contains and remove and everything, right? I don't have to just replicate this whole block of code. Does that make sense? All right. So then in my remove method, right? All I have is what I do if I find the right spot. So I'm gonna mark the current and set the predecessor next equal to the current next. Now what this means is the advantages to this are I go through the list without locking anything. When I think I've found what I want, right? Then I lock both the predecessor and the current. I check that they're both still unmarked and that one still points to the other. And that gives me the assurance that everything's going to work. All right. So that's a big advantage over hand locking because there's much less locking. And it's an advantage over optimistic because in optimistic we have to trace everything twice because we don't know. That's the only way we could know if the thing's deleted. Um, but then we go to the lock-free one. And the lock-free one is more complicated because what this is trying to do is it's trying to avoid any blocking code, right? I mean, if we have a lock, that's blocking code. So the mental test, just as a reminder for whether code is blocking, is if a thread were to go away, would the remaining threads be able to make progress, right? That's the thing you got to ask yourself if you want to find out whether something is blocking. So anyway, so lazy set is clearly blocking because it uses locks. But in this case, what we're doing is we have this atomic markable reference in the node. So we have a different node than in the other thing. yeah, the next field, which is down here for some reason. It's confusing to me. Why did I do that? I don't know. I can try. Well, how's that? Oh, wasn't expecting to get my allergies like that. Okay. All right. So the key thing is the atomic markable reference, right? Which is going to keep track of the mark bit as well as the reference in one object. All right. And then we need to do that because we need to update both things at once. So we're going to initialize the Sentinel. We're going to initialize the nodes with null and false here. And then when we go through the lock-free set, when we're gonna add, for example, we're gonna compare and set current. So the pred.next field is going to be set from the current to the node that we're adding, right? And we're going to check that the marked flag is set to false on the predecessor next field, and we're going to say that it remains false. So we're changing both of these at once. We're changing cur and false to node and false, right? So this lets us do two things at once. And likewise in the remove, we're going to do the same thing. We're going to say, when we're going to snip out we're going to go from the successor, we're going to get rid of the current one. So we're going to take the pred.next field from current to successor, and we're going to have false, false, right? And that's what we're doing. And what we did to snip the thing out, right? The fundamental delete operator was we did a current.next.attempt mark. So that is going to try to change the mark to true. That is, if the field is still, if cur.next is still successor, then it will change the mark to true. Okay. And that if that doesn't succeed, then we're going to do a retry. We're going to go back to this start of this loop and we're just start over because somebody's interfering with us. So we're just going to start again. And then this is the thing that actually does the physical delete. So we do the logical delete here, right? And if the logical delete fails, we start over. And then we try the physical delete. But if the physical delete fails, we don't do anything, right? And why don't we do anything? Well, it's possible that they did, but the reason we don't do anything is because we have this window method here, this window find method. And what the window find method is going to do is this is the thing that walks through the list and finds us our predecessor and current nodes, predecessor, current, and successor nodes. And what it's going to do is it's going to be looking, as it walks through the list, it's going to be looking for the marked nodes. And if it sees them, it's going to snip them out. Okay, so everything that walks through the list is attempting to clean it up as well. So that's why we don't need to worry about that too much, because we know it's going to get handled by this. Okay. Other questions?
When would you use these like over another? Like, is there a situation where?
Well, okay, so you always have to figure out what your workload looks like and test it. Because changing the workload is going to change which things work better. So you have to have a good idea of what that is and what the important parameters are. And you can't just know that without trying. In this case, I put in some artificial workloads, and I think for me, it's being slow for some reason. probably gave it a big enough set. So this is showing the timings for the different things. So there's the fine grain set, the lazy set. And the lazy set is a huge advantage over the fine grain set. In this test, the optimistic set won. It actually got the lowest timing. And that's in the times I've run this test, that is unusual. Let me run it again. It's clear that fine grains, though, is not the winner. It's the hand-over-hand method. Look at that. This time, lock-free set won. I've seen lazy set win a lot. And what am I running with this workload? Let me take a look at what I did. Okay, I didn't do it that way. Stop here. So I have 10 threads, 500 items per thread, is what I'm doing. And then here I have the various things that I'm doing. So I do a sequential test first with a few things, and then I start up my timer. I do the standard thing with an array of threads. I do a bunch of adds. I do a bunch of contains. I do a bunch of removes. I do add contain removes. I do a bunch of extra contains. And then I do a start and a join on all those things, and I get the current time. So that's the kind of test I came up with. And if I change these numbers around, I'll get different performance characteristics. So if I put in 3 here, I think, and 100 here, it'll run faster. And this time, lock-free set won. It's interesting. You know, when I was doing this before coming to the classroom, lazy set was almost always winning, and now it's not. So I know there are different property. I know that sometimes Java has different behavior characteristics depending on my network connection, and I'm not sure I understand why that is. But anyway, this is what it's doing now. Let me put 1,000 in here and try again. But when I was testing it outside of class, lazy set was pretty consistently beating lock-free set, which you know it's not supposed to do because lock-free is more sophisticated. But sometimes the less sophisticated thing wins, and you've just got to experiment. There's no substitute for that. Okay, so this time, right? This time, lazy set won. See, if I just keep trying enough different things in enough different ways, something different wins, right? So that's the lesson for you, is you have to tune your solution to your workload. This is going to be true whenever you have various different algorithms for doing something. You don't know what's best unless you run tests like this. Your analytical skills can only take you so far. Before experiment is the thing you have to rely on. All right. So, what else can I explain to you?
Is there something that comes after lock-free?
No. These are all the algorithms that we have for this chapter. All right, and these algorithms for the set here, this optimistic, lazy, lock-free. You may find, I expect that you will find in your life, if you go on to do parallel programming, you will see things that are similar to this, and that you'll be able to engineer one of these types of solutions to fit what you're doing. It's a pattern. These are patterns that kind of show up. But the thing I would strongly recommend staying away from is hand-over-hand locking. I believe that's fundamentally dangerous thing to do.
Can you explain why that's dangerous again?
Because locks are non-composable, right? And the safe way to use locks is if you have a critical section, you grab all the locks you're going to need before the critical section and you release them all at the end. If you start acquiring new locks inside the critical section, that you could get two threads doing them in the wrong order, and then you get deadlock. And there's no easy way out of that. You have to just understand what all your code is doing, what all the possible interactions are, and that's generally too hard for a human. So I think that hand-over-hand locking of the solutions here, it's the lowest performance, but I think it's also the most dangerous because of that.
So basically with all of these blocks too, we just want to have like a set of items that we can like add in and read and view, like that it's like atomic. So
Right. So the idea is we have a set, and we want to be able to add, remove, and check containment in high concurrency, right? So we want to be able to do that in high concurrency, and that's the thing that we're trying to optimize. So in answer to your other question, Reagan, there could be a situation if you were on a machine where you had threads that were unreliable, right? Where it was possible or expected that some of them would just stop working, then you would definitely want the lock-free one, because that one will always make progress even if other threads die. For any of the other ones, if threads die, that's it. It just shuts everything down.
So that's the only one that guarantees progress, even if none of them stop working.
Yes, because the problem is if you have any code with a lock in it, if somebody grabs that lock and does not release it, and they die while holding it, that's the end, right?
Well, when would it be a possibility that a thread dies and then just like instead of threads you have computers and like that goes offline or something, right?
Well, so the problem is threads are individual pieces of cores, right? So I don't know that I have ever in my life seen the thread go away. It's kind of hard for that to happen. It makes much more sense for a machine to go down than a single core to go down. I'm sure it has happened, but it's very rare. It's more useful. So the thing that can happen, right, is a core can become slow or it can be bogged down with something else. But we talk a lot about cores dying. Even though that's more of a theoretical thing, it's a thing that allows you to understand what blocking means, right? It's if you want to understand whether something is blocking, the way to do it is to pretend a core dies at an inconvenient time.
Helps us determine if we're dying like messes up our program. That's probably not.
Correct. If a core dying means your program can no longer make progress, it's blocking. And therefore it's either deadlock free or starvation free, but not lock free or wait free. Okay. Other questions? I think we had a homework question to go over still. Yeah, all right. So I had some trilocks, and all right, so the way I did this is I created an interface called Simple Trilock, which extends Simple Lock, right? So Simple Lock was the thing that has lock and unlock, and I added Boolean Trilock. And then inside Trilocks, I had some static classes that override things. So for my TTAS with Trilock, instead of doing the false true, I did a compare and set. Now you can do a single get and set here. It actually also works. In general, you're going to be replacing the get and sets with compare and sets, because the notion is that compare and set, if it fails, it doesn't change the state of, say, the tail in the Q node or the MCS lock, right? And that's what you need to happen, right? You can't afford to change the state if it fails. Now, in this case, if it fails with a get and set, it's just it was a true and it's updated to a true, and so nothing happens. But in the other cases, if you did that, it would damage the class. So the CLH with try-lock is going to do the predecessor K. It's going to get the predecessor. It's going to check the predecessor is not null and the predecessor is locked. And if that's the case, it's going to return false, right? And if it gets past that, then it's going to get the Q node. It's going to set the Q node to locked, and it's going to do a tail compare and set pred to Q node. And if it succeeds, then it's got the lock, and it says pred.set is pred and returns true, and otherwise it returns false. But the only place where it can potentially change things is here. And if it does, and if it changes it, then it's got the lock, and otherwise no. And the similar thing is happening with the MCS lock, right? We're going to, but this case, we know that if it's unlocked, it's got a null in the tail. So what we're going to do, what I did, is we did a tail compare and set from null to the Q node. And if we do that, we've got it. And that's that. And then I constructed some tests for this. So I do a try lock, and then I assert I make sure the two try locks in a row don't succeed, right? Because that would be bad. First one should succeed, second one shouldn't. Then I do an unlock, then it should succeed. Okay, and then I do an unlock. So this is just a basic test, non-concurrent test of the functionality, and it's doing what it's supposed to do. And then I create some threads, and I do. So what I do is I create a number of work items to do. I have attempts and I have successes, right? And if I succeed, then I unlock and so on. And then I'm going to go through here and print the number of attempts and the number of successes. And they shouldn't necessarily be equal, right? Because sometimes the try lock is going to succeed and sometimes it isn't. And what's kind of interesting to me when I run this, so they're work items. Let's take a look at work items. I have 5,000 over work sleep. So I have my artificial work unit in here that I do once I have so I have my artificial worker here, and it has this work unit. And what it does is it does an assert from working compare and set false to true. It sleeps for a while, then it changes it back. And the purpose of this is if I did have some kind of concurrency error, if say two threads got the lock somehow, right? Then this code would fail, right? Because one of them would come in and do this compare and set and go to sleep. Then the next one would come in and try to do the compare and set and it would fail. So I constructed this work test to catch that error. Now when I run it, so again, work sleep is 10, so I'm 10 milliseconds. So I have 500 work items, right? So when I run this, $500 successes, 5,000 attempts, right? For each of these locks, it's gonna do the same thing. And I guess what's happening is the length of the artificial work is causing everything to synchronize. So you have n threads. Each one attempts to get the lock, only one of them succeeds in each of these time unit things. And so I always wind up with 500 and 5,000. Anyway, that was my implementation of the homework. Again, you have to always test things. And the more ways you can think of to test them and the more aspects of them you can test, the better off you are. Never trust anything if you don't have to. Sometimes you have to trust things, but try not to. Any questions about any of that? All right. I have two things for you that we can do at this point. I have a quiz, which I would like to give at 4 o'clock, but I could also start on chapter 16.
If we start chapter 16, we still have to take the quiz at 4 o'clock?
Yes. Well, you're going to take I'm just saying, unless you've got more questions on this stuff, what I have for you next is chapter 16.
Slight question.
Okay.
So in chapter 9, on slide 115.
Hold on. Let me catch up to where you are. Chapter 9, slide 116?
115 and 16.
Oh, I'm sorry. I didn't put chapter 16 on the page. Look at that. I meant to do that. $115, this one?
Yeah. Going through optimistic locking.
Yes.
But it's a little confused. Can you
Okay.
go back over it?
Yeah, okay. So, well, let me do it. Let me do this. I don't know how you feel, but I always am happier with actual code. So what optimistic lock is going to do, so notice how my find method works for optimistic lock, right? What it's going to do is I have a while true loop. I'm going to get predecessor. I'm going to get a current node. I'm going to say while the current key is less than the key, predecessor equals the cur equals cur.next. So far, that's all standard, except nothing is getting locked, right? And so once I've got my predecessor and my current, then I lock them both, and I'm going to get a new node and initialize it from the head, and I'm going to call it x. I'm going to say while x.key is less than pred.key, x equal x.next. So what I'm doing is I'm starting from the head and making sure I can still get to predecessor. Okay, and if I get to predecessor and predecessor dot and if I get to predecessor and predecessor dot next is still equal to cur, then I found the thing. Okay, so what I have to do is with optimist. Okay, so what I've done, right, is first I trace through the list without locking, and then I lock, and then I trace that I can still get from the head to the predecessor while I'm holding the lock. Okay, because I need to know if that predecessor if that predecessor has been deleted, right? I need to know right now because I'm ready to do my thing. So I have to retrace it, and then if I go through this loop and I didn't find the predecessor, that means it was deleted. And if the predecessor dot next isn't the cur, then something got added or removed. And so I'm just going to bail. I'm going to hit continue, and continue will take me back to this while loop, and it'll try again. But if I get past this, that means that first I went through without the lock, then I locked it and retraced it and made sure it hadn't changed on me. Now I have confidence that I can do my add or remove or whatever. That make sense? What can we do to move it up from a little bit?
I think I get it. I'm just kind of confused on why you would go back over the.
Because if you don't go back, you don't know whether predecessor. Okay, so let's look at the slides.
By like going.
I'm not sure what you mean by it.
If you need to verify that you can get somewhere, why wouldn't you just like mark it and then go over the list?
Well, we have no way to mark it. We didn't put a field in there for that. I mean, and if we did, what would we do? Put I'm reserving this one. What would It's just,
silly to me to like get there and then go all the way back through the list to make sure that you can still get there.
yes, okay, so it does seem silly to trace the list twice to do anything. I agree. But it has been discovered that in many cases, right, that doing this twice is worth the cost, even though even though you're doing something twice, there's a considerable overhead added with locking and blocking and so forth. And if you're doing less of that, but actually retrace the list, it still sometimes pays off. And we saw that in our timing tests, right?
It happened between the time that you trace it the first time and make it there. Couldn't something still theoretically happen?
No, because I've locked it. Nothing can modify in the optimistic set. Nothing can be modified without locks. The only thing you can do without locks is read. Okay, and so what you do when you want to modify something is you read it, you find what you think you want, right? Then you lock it, make sure you got what you expected to get, and then you do your thing.
It makes more sense now that you can't modify anything else without the lock.
Right. So, and this optimistic notion of doing things, where you do things without any locks and you're only reading, and then after you think you found something that a place where you want to make a modification, only then you lock things and make sure, right? This is a general technique that people use in databases and so forth. This sort of optimistic way of doing things. In fact, your CPU will, when it encounters an if statement, will sometimes start executing the code inside the if statement in advance of evaluating the truth of the thing up in front. And if it turns out not to be true, then it just discards what it did. Because sometimes that gives you a speed up.
And validation here, just making sure that you can get back to it.
Mm-hmm. Validation is just making sure that this is the validation, this piece right here. I guess in my code, I don't have validate as an independent method like they do. I guess I changed that. I probably ought not to have, but that's what I did.
Lazy method is kind of just like putting a sticky note on something that says like deleted.
Yes. And that's my favorite. If I have to pick a favorite, lazy is my favorite because it is because I think putting the mark bit there makes it finally clear what's going on, right? It's the least complicated of the highly parallel methods. It's not as sophisticated as the lazy set, but sometimes simplicity is an advantage. So I would call it my favorite.
Section in here about abstract data types. I don't know what that's for.
Where?
Slide 32.
Slide 32. Abstract data types. I don't remember that. Oh, okay. So what they're doing, right, is they're saying abstractly, you can think of this thing that we're doing as this mathematical set, right? And that set has properties that are independent of the actual, we describe this set and the behavior we want in a highly abstract way, and don't worry about how we're going to implement it. Now, we choose to implement it with a linked list, but in principle, there are 100 other ways we could probably have done it. And so this is the abstract way is the mathematical way, and the concrete representation is the coding way. It's the implementation. So abstract is high-level behavior, and concrete is implementation details. The other important thing to get out of this is the concept of invariance. Invariance can be very useful for classes and objects that you make. You figure out things that you want always to be true, and then you make sure they're always true with each method call. And that gives you the ability to reason about their behavior. That's nice to have.
Is everything we've done so far coarse grain locking up to this chapter?
I have to go back and look at what we've done. I don't think that's quite true. So we've done, well, okay, so what we've done is let's look at the syllabus. So in chapter 1, we just talked about the basic locking at a theoretical level, right? So that was and then we sort of introduced the Peterson lock in terms of cans and flags. And I am in the wrong course. And we introduced the Peterson lock in terms of that. We also in chapter 8 we discussed all kinds of various locking strategies. I wouldn't call all of those coarse-grained. So we had reader-writer locks, for example, and that's kind of a fine-grained if you want to think about it. It's not quite the right description for it, I don't think. But what we talked about in there was various kinds of synchronization data structures. We had semaphores and we had reentrant locks, and we had queues. And our queues were, I guess you would call those coarse-grained locked objects, right? Because we have one lock for the whole object. So I guess those would fit that description. So then we discussed how to implement locks, and we had memory-only locks, and we discussed consistency, consensus. We did consensus. Consensus isn't even locking, right? It's explicitly wait-free. And then we talked about lock implementations and how we do them once we have RMW instructions. I wouldn't call that coarse-grained locking. I just call that locking. And then we had our midterm, and then we did the linked lists. So, I mean, I think that we have had some coarse-grained locking. I wouldn't describe it as all that.
Hand over hand is fine grained as any of the other locks.
We don't call them that normally, so we call them by their other names. So fine-grained, it's going to take lots of little. It's gonna lock lots of times in small increments, right? That's what we're getting at when we say fine-grained. Now, optimistic is still going to get these predecessor and current individual locks as opposed to a coarse-grained lock. But we're calling it optimistic because we're first tracing it without doing this. We're just thinking of this in a different way. So if you prefer hand over hand to fine-grained, you could maybe think of it that way. We're just looking for ways to distinguish these sets. But yeah, okay. Any other questions?
Is there anything we need to know for this quiz?
Yes. You need to know stuff from,
Specific?
yes, chapter 9.
Guys,
I'm not going to give you the questions that are on the quiz.
Is there any choice do one of the coding boxes?
Something like that.
Can we go over that specific method?
No.
Give me a hint of which one it is.
It's one of the sets. I'll give you a hint. It's not the coarse-grained. It's one of the more difficult ones.
That's not helpful.
All right.
Whole slides of snippets of code.
Well, hopefully, if you've been paying attention and it's been making sense, you'll be able to figure out what to do. The goal isn't for you to memorize huge blocks of code, right? The goal is to put basic understandings in your head that you can reason about. And maybe you don't get everything perfect, but you get it, mostly on track. And you can, eliminate the pitfalls for the for the people who aren't paying attention that get thrown in.
I pay attention. I'm just bad at filling the blank code.
Well,
So I can't like test it. Like if I could
I-
sit there and
I
test it-
understand. I understand. I picked that CLH lock on the test because it had, just a small number of methods with no control flow in them, so I just one after the other. But grading it turned out to be a little harder than I wanted it to be, but that's life. But it wasn't so bad because we have a small class. If I had 100 students and I gave a problem like that, I would be grading it for hours. Calvin, do you have any questions?
There like a summary for each different module in this chapter?
I think they kind of go through it in two levels. So first they go through it at high level, and then they go through all the details. So the summaries are kind of at the beginning. So we do coarse grained, right? We say each of the locks stand in line, and we have like this. We talk about the things, and then we have the fine grained synchronization. And instead of a single lock, we split into independent ones. And then we have optimistic, or we have lazy, or we have lock free. So we have in those slides, that set of slides, we have a summary of their characteristics and behaviors. Who wants to see stuff about chapter 16?
I want to have the window class.
Okay, let's take a look at the window class. I mean, we've slide 223, you say?
Yes.
Here we go. So the window class is just a class for finding the predecessor and the current. If I may, here's my implementation of the window class. I prefer my implementations of things if I can, because the slides always have funny little problems with them. So in this case, we just have, one of the problems they have is they leave off the abstract types. So I have the predecessor and the current node is what I'm trying to find, and I can instantiate one with a predecessor and a current node, like that. But the idea is that normally my find method is going to start with the head and the key that I'm searching for. And it has this while loop, and it's going to say while pred.next.get reference, right? That's going to get the current. So because this is an atomic markable reference, we can't just say pred.next. We need to say pred.next.get reference. And then what we're going to do is we're going to get the successor, and we're going to find the current, whether the current node is marked. And while it is marked, we're going to try to snip it out. So we're saying the predecessor.next is going to compare and set the current to the successor with false, false, meaning unmarked, unmarked. And if that snip fails, then we're going to retry, which means we go back up to here and start from the head again. Okay, so what happens is if there's lots of contention in the list, this method here might fail multiple times and restart. But if it doesn't fail, right, if the snip succeeds, then I can march forward. I can say, current equals successor, successor equal current.next.get marked. And here again, we're filling in the marked bit. So we might stay in the loop if that happens. So we're deleting things as we go through. But if we get past that while loop, right, if we find things that aren't marked, then we just keep going. If the current key is greater than or equal to the key, then we return the window with predecessor and current. Otherwise, we update predecessor and current. Does that make sense? It is tricky. I won't deny that to you. This particular code is so, I think that like CLH lock or Peterson lock, right? These are things that you can probably go home and code from memory with a little fooling around and not a whole lot of struggling. But if you went home and tried to code this from memory, I think you'd struggle. I know I would. I mean, this is the thing that you have to stare at hard and ponder, right? Yes, Tristan.
So, first question, this is part of the weight-free implementation.
Lock-free,
Sorry.
not weight-free.
Um, and so this is run every time we want to find something in the list, so this will like find the two nodes and delete marked nodes to get rid of them.
Oh, yeah, if there are if there are deleted nodes in our path, it will get rid of them.
So it only, so when we go and delete something, we will like mark it as deleted, and then as we're going by the delete.
Right. So when we do the delete, right, we mark it deleted. And then if we don't succeed at marking it deleted, then with our remove method, then we retry in that method. But on the other hand, but then the next step, right, where we actually snip the links, right, where they go from predecessor.next to current.next, we only try that once. And if it fails, we just don't worry about it, right? Because we know that this method is going to clean it up for us. But we try to do it, but sort of half-heartedly.
Just to summarize then, like, this is weight free because
It's lock-free.
sorry, lock free. Lock free, right? And the reason why it's lock free is because it will try it once, but it doesn't wait for any other threads to get out or do anything. It just marks it and then tries it. If it doesn't work, then we'll just return.
Yeah, and the thing to remember about lock-free versus weight-free, if it has a while loop in it, then it's probably not weight-free.
Yeah, so it's not weight free because it'll keep trying until it does eventually work.
Right, it could try an arbitrary number of times, and that's what a while loop is kind of telling you. Yeah, I mean, you have to think about it a little harder than that, but when you see a while loop, you should be thinking, I'm not weight-free.
But you're wild free.
Yeah, especially while true. That's a big red flag. All right. Any other questions? Anyway, I would just sort of know at high level how window worked. I wouldn't struggle with the details. Any other questions?
How is the lock free different from the lazy then? So the lazy.
So the lock-free, the lazy one locks. The lazy one uses locks. So it is explicitly not lock-free.
The difference there is that on removal it'll lock and then remove rather than like,
That's right. And lazy set is not going to do this window class business. It just has a normal, it just does a lock-free traversal of the list. When it finds the two nodes it wants, it locks them, checks they're both unmarked, and that one still points to the other, and then it knows it's good to go. It's one of the highest performance. It's one of the simplest, you know. Coarse grained being the simplest.
we mark the nodes, and the reason why lazy works is that you mark it and then you lock it to remove, right? But if something is trying to simultaneously work on the nodes,
We're-
the marking will tell it if it's like been deleted or not, even if it, like, without having to check if it's been reachable or not. It just
Right.
has a mark that tells it that it's reachable.
Right.
Okay, that makes sense. That's different from optimistic because we don't have the mark this. Optimistic will check all the way.
It'll retrace, yes.
Yeah, it'll keep retrying.
But optimistic also locks. The only one that doesn't lock is the lock-free one. It's all pretty cool stuff.
Just hard to wrap the brain. A lot of material. There's a lot of like.
There's a lot of stuff in this course. And there's still a lot more stuff in this course. So we will make your heads really hurt by the time it's over.
Yeah, I would love to see like, you know, where all of this could be used and
I mean, so different things are useful in different places. And I have definitely learned things myself by teaching this course. Been forced to think about things in different ways. Like I have my 2 counter lock, which I came up with, which I never would have thought about if I hadn't decided to teach a parallel course and talk about lock implementations, right? And scrutinize those. But it takes your focus in different ways. It makes you think about different ways of doing things. I feel like there's, I look at all the stuff we do in this course, and I feel like there's some kind of analytical, some kind of calculus, some kind of analytical method hiding behind the more haphazard reasoning that we're doing that I can't quite get my brain around. I feel like it almost makes sense. Some kind of special way of doing the reasoning about parallelism that, well, I feel like there's some easier way of doing all this that I can almost grasp, but maybe it's just my imagination. My intuition tells me there's some clever way of analyzing things to understand how all these pieces can, how these parallel algorithms can be done, but it's just can't quite get it. But I do have something that I did invent because of this course, and we are going to talk about in future classes. A couple of things actually. So
it almost feels like most of the topics that we learn in this course, like things happen in parallel programming that would never happen in single threading. And it's like,
right.
It's almost like the world as you knew it before coming into this class.
Yes.
Just like nothing makes sense. Everything's like, up is down, left is right.
Yes. That's what parallel programming is like. Up is down, left is right. And then what is it Douglas Adams says? The logic guy proves that God doesn't exist, then he proves black is white, and he says that was easy, and then he gets killed at the next zebra crossing. Anyway, so the problem is all machines now are parallel, and the further in time we go, the more parallel they are. And if you don't get a grasp of parallel programming, you're going to be fumbling in the dark. So everybody needs it, I think. If you're going to program, you need to understand parallel programming. And if you don't have a course in it specifically, you're just going to sort of fumble onto some very rudimentary understandings, and you will be ill prepared to deal with anything serious. All right, I'll just give you the quiz. I understand that you don't want to hear 16 yet. We only have like 5 minutes.
My brain hurts already. I don't want to learn words.
All right. I wish everybody had shown up, but only the people that want to pass are here, I guess.